One night he was tracking thunderstorms 600 miles away, but all of a sudden he heard these beeps, and it was 3 beats in sequence. And the more he thought about it, he thought that they came from outer space.
In 1899, while conducting wireless transmission experiments in Colorado Springs, Nikola Tesla noticed something unusual in his instruments. What first sounded like random electrical noise appeared to form repeating patterns, almost like counting 1, 2, 3. At the time, the idea of signals from space seemed impossible. Tesla believed he may have intercepted a message from beyond Earth. The mystery remained buried for decades, but today, new speculation has emerged, this time involving Google's powerful quantum computers. The discovery. In 1899, Nikola Tesla moved his research to Colorado Springs, a location he believed was ideal for studying high-voltage electricity and wireless transmission. The area's thin air and frequent lightning storms made it a natural laboratory for experimenting with powerful electrical currents. Here, he built a large experimental station, complete with massive coils and antennas designed to send electrical energy through the atmosphere and possibly across the Earth itself. At the time, Tesla was obsessed with a bold idea: transmitting information and power wirelessly over long distances. This work would later inspire projects like the famous Wardenclyffe Tower, his unfinished attempt to create a global wireless communication system. But in Colorado Springs, Tesla wasn't just transmitting signals, he was also listening. Using highly sensitive radio receivers of his own design, Tesla began monitoring electromagnetic activity in the atmosphere. It was during one of these listening sessions that he noticed something unusual. Instead of the random crackles and bursts typically produced by lightning or natural electrical disturbances, his equipment picked up signals that appeared to follow a pattern. According to Tesla's notes, the pulses seemed to occur in regular intervals. They weren't chaotic. Instead, they had rhythm and repetition. Tesla described them as a sequence of distinct signals that appeared almost intentional. In later interviews, he claimed the pulses resembled a form of counting. As life-altering as his finding was, at the turn of the 20th century, this was a rather startling observation, and this meant not many people would take the idea seriously. At the time, even radio communication was still in its infancy. Inventors such as Guglielmo Marconi were only beginning to experiment with wireless signals. So, the idea that a receiver could pick up structured transmissions from beyond Earth was far outside the scientific thinking of the era. But Tesla allowed himself to consider the possibility. In an article published a few years later, he suggested that the signals might represent an intelligent message. He speculated that if humanity ever made contact with another civilization, it would likely begin with simple numerical patterns, something universally recognizable. Today, that statement sounds eerily similar to modern ideas about interstellar communication. Decades later, scientists working in the field of the SETI Institute would use a similar principle when searching for extraterrestrial signals. Look for patterns that nature alone would be unlikely to produce. However, many scientists of Tesla's era were skeptical. Some believed the signals were nothing more than natural atmospheric noise. Others argued that Tesla may have accidentally intercepted early wireless transmissions from nearby experiments. Without more advanced equipment, it was impossible to determine the true source. What made the situation even more mysterious was Tesla's reputation. He was widely respected as a brilliant engineer, the man behind revolutionary work on alternating current and high-frequency electrical systems. But by the early 1900s, some critics believed he was drifting into increasingly speculative territory. As a result, the strange signals he reported were never thoroughly investigated. They became one more footnote in the long and complicated legacy of Tesla's work. For decades, the story remained largely forgotten, but in recent years, as scientists began to push the boundaries of computing and quantum physics, Tesla's strange observation resurfaced in unexpected ways. Could Tesla have detected something far more significant than anyone realized at the time? Quantum computers. More than a century after Tesla described those strange signals in Colorado Springs, science has entered a completely different technological era. Today, researchers are no longer limited to analog receivers and electrical coils. They now have access to machines capable of processing information in ways Tesla could never have imagined. Quantum computers. Unlike traditional computers, which store information as bits that exist as either a 0 or a 1, quantum computers rely on units known as qubits. These qubits operate according to the rules of quantum mechanics, allowing them to exist in multiple states at once through a phenomenon known as superposition. Combined with another quantum effect called entanglement, this allows quantum systems to explore enormous numbers of possibilities simultaneously. For decades, quantum computing remained largely theoretical. The mathematics worked on paper, but building a stable machine proved extremely difficult. Why? Because qubits are incredibly fragile. Even tiny disturbances from heat, electromagnetic radiation, or vibrations can cause them to lose their quantum state, a problem known as decoherence. Despite these challenges, major technology companies have invested heavily in the field. One of the most prominent efforts has come from Google, whose quantum research team has spent years developing experimental processors designed to demonstrate what scientists call quantum advantage. In 2019, Google announced that its quantum processor, known as the Sycamore quantum processor, had performed a highly specialized calculation in about 3 minutes. According to the company, the same task would take a traditional supercomputer thousands of years to complete. The announcement sparked intense debate within the scientific community, but it also marked a turning point. Quantum computing was no longer just theoretical, it was becoming operational. These machines operate under extreme conditions. Quantum processors are typically housed inside elaborate cryogenic systems that cool the hardware to temperatures only fractions of a degree above absolute zero. At those temperatures, electrical resistance and environmental noise are minimized, allowing qubits to maintain their delicate quantum states long enough to perform calculations. But the true potential of quantum computers isn't just raw speed. Their real strength lies in their ability to simulate complex systems, things that are nearly impossible for classical computers to model accurately. This includes problems in chemistry, material science, cryptography, and even the fundamental behavior of particles in the universe. Quantum simulations can recreate interactions between particles, fields, and forces with unprecedented precision. And this is where things start to get interesting. Some researchers have begun using quantum processors to simulate electromagnetic systems and signal behavior at incredibly fine scales. In simple terms, these machines can analyze patterns in waves and fields in ways that traditional computing methods struggle to replicate. As quantum experiments became more advanced, researchers began encountering patterns and fluctuations in their simulations, tiny bursts of signals that appeared structured rather than purely random. Most physicists interpret these patterns as expected artifacts of quantum systems. After all, quantum mechanics is fundamentally probabilistic. Strange fluctuations are part of the territory. However, outside the scientific community, some observers began drawing connections between these unusual patterns and historical reports of unexplained signals, particularly those described by Tesla in 1899. This raises a provocative question. If Tesla truly observed a repeating electromagnetic pattern more than a century ago, what exactly was he detecting? Was it simply atmospheric interference, an early wireless transmission from another experiment? Or could it have been a natural cosmic signal, something humanity would only begin to understand decades later with the rise of radio astronomy? The experiment. At the center of Google's quantum computing effort is a scientist named Hartmut Neven. A computer scientist and physicist, Hartmut leads the quantum AI division at Google and has spent years pushing a technology that many experts once believed would take decades to build. Unlike conventional computing labs filled with racks of processors and blinking servers, the machines Hartmut's team works with look more like experimental physics equipment than computers. Inside Google's quantum research facility in Santa Barbara, California, the processors sit inside towering cryogenic refrigerators, multi-layered metal chambers designed to cool the system to temperatures just above absolute zero. At those temperatures, the strange rules of quantum mechanics can operate without being constantly disrupted by environmental noise. The chip itself, small, delicate, and threaded with superconducting circuits, barely resembles the processors inside a smartphone or laptop. Yet within this tiny device, qubits interact in ways that allow researchers to study phenomena that classical computers struggle to model. One of the goals of Hartmut's team has been to understand how information behaves inside these quantum systems. When qubits interact, information spreads through the system in complex patterns that physicists sometimes compare to ripples moving across a pond. To study this behavior, researchers run what are known as quantum echo experiments. In these experiments, scientists send information through a quantum circuit and then attempt to reverse the process, essentially asking the system to retrace its own steps. By measuring what returns, researchers can see how information moved through the network of qubits and how errors developed along the way. This may sound abstract, but the experiment serves a very practical purpose. Quantum computers are extremely sensitive machines, and even the smallest disturbances can corrupt calculations. Understanding how signals evolve and degrade inside the system is crucial for building reliable quantum hardware, and that's exactly what Hartmut's team has been trying to solve. In fact, much of Google's recent quantum research has focused on improving quantum error correction, a method that spreads information across multiple qubits so that mistakes can be detected and corrected before they destroy a computation. This work builds on earlier breakthroughs involving Google's experimental Sycamore quantum processor in 2019. It had performed a specialized calculation that would have been practically impossible for classical supercomputers to reproduce in a reasonable timeframe. The achievement sparked both excitement and skepticism within the scientific community. Some researchers questioned whether the comparison with classical supercomputers was entirely fair. Others argued that, even if the calculation was highly specific, it still demonstrated something remarkable. Quantum machines were beginning to outperform traditional ones in certain tasks. But Hartmut's long-term vision goes beyond single demonstrations. His team is trying to build quantum systems capable of simulating physical processes so complex that traditional computers cannot handle them. These simulations could eventually help scientists understand new materials, chemical reactions, and even the behavior of fundamental particles. In other words, quantum computers are becoming tools not just for calculation, but for exploration. As researchers run more experiments on these processors, they generate enormous volumes of data, measurements of how signals move, fluctuate, and interact within the quantum system. To physicists, these patterns are simply part of studying an incredibly complex machine. But outside the laboratory, those same patterns have sparked something else entirely: curiosity. Because whenever strange signals appear in scientific experiments, people inevitably begin looking for deeper meanings. And when those signals involve electromagnetic patterns, the story begins to intersect with something far older, something that dates back to a lonely laboratory in Colorado Springs more than a century ago. The moment when Tesla first noticed a signal that seemed too organized to be random. Whether the two stories are connected is another question entirely. But the parallel has been enough to reignite one of the most enduring mysteries in the history of science, and that's probably why scientists are interested in tech once again. Why scientists are interested in Tesla again. Even though the idea that Tesla detected an alien transmission has never been confirmed, scientists still take his work seriously for a different reason. Many of his experiments were decades ahead of the scientific tools available at the time. Tesla was not just an inventor, he was an experimentalist who pushed electricity to extremes that few researchers had attempted before him. At the end of the 19th century, he was already working with high-frequency electrical currents, powerful electromagnetic fields, and early wireless transmission systems. Some of these ideas would later become the foundation for technologies that define modern life. One of Tesla's most important contributions was his work on alternating current power systems. His designs helped make long-distance electricity transmission practical and laid the groundwork for modern power grids. But Tesla's ambitions went far beyond lighting cities. He believed electricity could be transmitted through the air and even through the Earth itself. That belief led him to pursue experiments in wireless energy transfer. His most famous attempt to demonstrate this concept was the construction of Wardenclyffe Tower in New York, an enormous experimental structure intended to transmit signals and possibly electrical power across vast distances without wires. The project ultimately failed due to financial and technical limitations, but the underlying idea of wireless communication did not disappear. In fact, the modern world now depends heavily on it. Today's technologies, from radio broadcasting to satellite communication, owe something to the early experiments conducted by Tesla and his contemporaries. Scientists studying the history of electromagnetism often revisit his work because it captures a moment when researchers were exploring electrical phenomena without the theoretical framework that would later explain them. That context matters when looking at Tesla's mysterious signal. When Tesla reported detecting unusual repeating pulses during his experiments in Colorado Springs, the scientific community had no concept of radio astronomy. The idea that stars, planets, or other cosmic objects could emit detectable radio waves had not yet entered mainstream science. It would take several more decades before researchers discovered that the universe is full of natural radio signals. In the 20th century, scientists began detecting radio emissions from a variety of astronomical sources. Some came from the sun, others came from distant galaxies. One of the most dramatic discoveries arrived in 1967, when astronomers first detected pulsars, rapidly spinning neutron stars that emit incredibly regular bursts of radio energy. When pulsars were first discovered, the signals were so perfectly timed that researchers briefly considered the possibility that they might be artificial. The pulses were so precise that the first one detected was jokingly labeled LGM, short for Little Green Men. Although scientists quickly determined that pulsars are natural objects, the discovery demonstrated something important. The universe is capable of producing highly structured electromagnetic signals. This realization has led some historians of science to reconsider Tesla's 1899 observations. While there is no evidence that he detected a pulsar or any specific cosmic source, it is possible that his instruments were sensitive enough to pick up natural radio phenomena that scientists would only begin to understand decades later. For modern researchers, Tesla's notebooks represent something fascinating. Perhaps not proof of extraterrestrial contact, but a glimpse into an era when scientists were encountering signals they did not yet have the language to explain. And sometimes, when new technology allows scientists to revisit old mysteries, those early observations begin to look less like speculation and more like the first clues of discoveries that had not yet been made. The striking similarity between Tesla's century-old observations and the patterns now emerging in quantum experiments has also reignited interest in the enigmatic inventor. While Google's quantum computers have not actually detected signals from beyond Earth, the parallels between Tesla's notes and modern data are too intriguing for scientists and historians to ignore. Tesla's experiments were far ahead of their time. In Colorado Springs, he pushed the limits of electrical experimentation, working with high-frequency currents, massive electromagnetic fields, and early wireless transmissions. His goal was ambitious, and today, researchers study his notebooks not for evidence of extraterrestrial contact, but for insights into early electromagnetic experimentation. Modern physics allows scientists to reinterpret Tesla's work in ways that were impossible a century ago. Some of the pulses he recorded may have been natural phenomena, like early radio emissions from cosmic sources or atmospheric effects. Yet the precision of his observations, recognizing patterns in what most would have considered random noise, demonstrates a keen experimental intuition that resonates with contemporary quantum research. And this is where Google's quantum computers enter the conversation. These machines operate on principles Tesla could barely have imagined. Qubits that exist in multiple states simultaneously, entanglement that links particles over distances, and the ability to simulate systems too complex for classical computers. Experiments like quantum echoes allow researchers to send information through a processor and then reverse it, observing how data moves and evolves. The result is often highly structured, intricate patterns, echoes of information that appear organized but are entirely generated within the quantum system. To physicists, these patterns are simply the expected behavior of quantum mechanics. But when seen through the lens of Tesla's Colorado Springs experiments, they invite a different perspective. Could some of Tesla's signals have been analogous to the fluctuations now observable in highly controlled quantum environments? Was he, in effect, glimpsing phenomena that only modern tools can fully explore? While there is no verified connection between Tesla's signals and today's quantum experiments, the coincidence points at something deeper. Great discoveries often emerge long before technology can fully understand them. Tesla's notebooks, once dismissed as eccentric, now offer a bridge between historical curiosity and cutting-edge science. As quantum computers become more sophisticated, they may allow researchers to simulate and analyze phenomena that were previously invisible, revisiting mysteries Tesla encountered with unprecedented precision. And while the idea of a message from the stars remains speculative, the intersection of Tesla's visionary work and modern quantum research is evidence of a broader truth. Sometimes, science only catches up to genius decades, or even a century, after the fact. As fascinating as it is to imagine that Tesla intercepted signals from the stars, the truth is just as compelling. His notebooks capture the mind of a man decades ahead of his time, experimenting at the limits of what was possible with the technology he had. Today, Google's quantum computers explore the universe in ways Tesla could only dream of, revealing complex patterns and behaviors that challenge our understanding of physics itself. What are your thoughts on this one? Tell us in the comments below. Thanks for watching. Please leave a like and subscribe to the channel for more videos like this.